Hi everyone, my focus on this project was understanding swarm logic and collaboration, and the work was heavily inspired by Xenobot research we learned about in class. I simplified these cells into mass spring systems to allow differentiable robotics, and within each cell are actuated springs and objects that can be propelled, mimicking ciliary propulsion. In the simulation, the aim is to clump orange cells, however, only the green cells are able to move, forcing them to collaborate to achieve the goal. It's important to note that each cell has their own brain with shared identical weights, but unique sensor values and unique motor control outputs. The A/B testing that I decided to look at was understanding complexity, as I showed earlier, and how that affects model trainability. I found it was really difficult to tell which model was definitively better, but the single node, less complex model seemed to perform slightly better overall. Generally, the initial training was terrible and resulted in a lot of perverse instantiation regardless of regularization I applied, so I decided to take a step back and look into some evolutionary algorithms to see if they could perform better with initial green cell conformational changes. And so, looking at the performances that are coming up right now, we're able to see that the circular array robot does perform the best up in the top right compared to the preformed bot in the bottom. I also want to note that without auto differentiation, this evolutionary approach took less than an hour to train compared to 8 hours for the differentiable approach. Overall, I do need to look into the loss curves to give more insight. And so here's the combined loss curve where the Y scale is log scaled. I also want to note that the preformed robot did perform the best, but it's insignificant compared to the round evolutionary bot. Also, it was interesting to see that the only bot that seemed to really learn was a square robot, and I think it might be because the less complex bots don't have sufficient sensors that truly affect performance. The objectives across these tests were to clump orange cells, keep everything on the screen, and penalize the overuse of spring actuation. The training curves don't really look too useful, so I decided to step back to a WAN-B approach and quantify the learning that I felt was visually evident. The blue bar shows that complexity does affect file performance, but orange shows that much of the performance is based on initial luck, and I think this is due to the less complex bots skewing data. I also ran some correlation analysis and saw that the higher complexity generally increased most of the losses, with one exception in pushing orange cells towards the center. Because the high orange bar showing the clumping loss, I think that this purple bar might indicate that the simpler robots trained to clump elsewhere in the simulator. In conclusion, this overall project was really difficult, and I spent a lot more time fixing the physics of the simulator as opposed to fine-tuning the agents. And moving forward, I would really like to look into differentiable physics implementations or switch to fully evolutionary approaches, possibly like voxelcraft.